Hello, and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 3, Lesson number 8, on the algebraic definition of continuity. Alright, this is kind of exciting because this is the point in the unit on limits and continuity where it all kind of comes together. How we use the definition of a limit to establish whether or not a function is continuous at a particular value of x. But before we introduce that idea, let's first look at the geometric definition of continuity one more time. Alright, a function f of x is continuous at an interior point in its domain, we'll talk about that in a second, x equals c, if it can be drawn at c without picking up your drawing instrument. Alright, so just really quick, an interior point. So let's say that we had f of x and its domain was, let's say, from -3 to 8 inclusive, okay? So an interior point is any x on the interval -3 to 8, right? Notice parentheses now. So basically an interior point is every point except for the endpoints, the left endpoint and the right endpoint. An interior point is any other one. So again, remember, a function is continuous geometrically if it can be drawn without picking up your drawing instrument. Okay? So let's jump in to the first exercise where we develop the limit definition of continuity. Alright, exercise 1, given the following function, y equals f of x, defined on the interval -2 to 2, right? Based on the geometric definition of continuity, list all values of x on the open interval -2 to 2 where f of x is discontinuous. So again, what that means in letter A is that I don't want you to think about x equals -2 and I don't want you to think about x equals +2, but list all other values where f of x is discontinuous. Pause the video now and make that list. Alright, well, if I were drawing this function, I'd kind of move along and I'd have to pick up my pencil here and then put it back down, so that would give me x equals -1, and then I'd keep coming down and then I'd have to pick up my pencil and then put it back down, so that would give me x equals 0. Then I'd move along, pick up my pencil, draw on this dot, come back, and there we go. Alright, so at -1, 0, and 2, we have discontinuities, right? Little star, and little star. All right. Now, letter B, C, and D are all very, very important, okay, because they're going to walk us through 3 distinctly different types of discontinuities. Letter B, at which discontinuity does the function exist, but the limit does not? Think about that for a minute. So the function exists, but the limit does not exist. Well, and that's at x equals 0, right? Because at x equals 0, g of 0 is 0, but the limit of g of x as x comes into 0 from the left doesn't equal the limit of g of x as x goes to 0 from the right, right? So we're going to different places. So the function exists, but it's discontinuous because the limit doesn't exist. Letter C asks, at which discontinuity does the limit exist, but the function does not? Think about this for a moment. All right, and that is at x equals -1, right? There is no way to give a value for this. G of -1 doesn't exist, but the limit of g of x as x goes to -1, regardless of whether it's from the left or the right, is equal to 1. Finally, letter D, at which discontinuity do both the function and limit exist? Why is there a discontinuity at this location, even though they both exist? Well, there's only one left, so that's at x equals 1, right? And that's, oops, not f, Kirk, g, sorry. G of 1 is 0. The limit of g of x as x goes to 1 is 1. So why is there a discontinuity? They both exist. There's a discontinuity because the limit of g of x as x goes to 1 doesn't equal g of 1, right? Now, what letter B, C, and D get into is a very kind of concrete way of knowing whether or not a function is continuous at a particular value of x. See, at the vast majority of the values of x, let me do one in red. Let's pick this one right here. At the vast majority of the values of x, whatever that is, right, the limit exists, the function exists, and they're equal to each other. And that's because it's continuous there. So we're going to give an algebraic definition of continuity in the next screen. So pause the video now and write down anything you need to. All right, I'm going to clear out the text. Let's move on. Algebraic definition of continuity. A function f of x is continuous at an interior point in its domain, x equals c, if and only if the limit of f of x as x goes to c is equal to f of c, right? And that's it, right? That's the whole deal, which is really, really kind of cool. If where we are headed equals where we end up, then we say that we're continuous. And if it doesn't, then it's not continuous. And of course, this definition can fail in a variety of ways. You know, the simplest ways is that it's just not equal. You know, this is one number, this is another number, and they're not the same number. The more subtle way is if the limit doesn't exist, so if the limit of f of x as x goes to c doesn't exist, or if f of c doesn't exist, or if they both don't exist, because that can happen as well. You know, that could happen if we had something that looked like this, right? So the limit doesn't exist, the function doesn't exist. So every time you have a discontinuity, in some way, this equation, this master equation here, gets violated. Okay, and we'll look at that more in just a bit. Okay, but that is the algebraic definition now of what it means to be continuous at a particular value of x. Now, exercise 2 is of only minor importance, but let's make sure to get it out. It says why and how do we have to modify this definition to make it fit the endpoints of the domain? And let me be very clear about what I mean by this. If I had some function like this, all right, and let's say I began at A and I ended at B, and it looked like this, right, nice and continuous everywhere. All right. I want to be able to say it's continuous everywhere. I want to be able to say it's continuous on A to B. All right. But what's the problem with this definition? This guy right here circled in blue. Why can't I apply that on here? Think about that for a minute. Pause the video if you need to. All right. Well, the problem with that is that the limit of f of x as x goes to A and the limit of f of x as x goes to B, well, they both don't exist. So by default, that definition breaks down, right? I mean, we would say, well, it's discontinuous there. Now, a lot of people would feel comfortable with that because when we begin or when we end this drawing at A and B, we have to sort of, if you will, pick our pencil up. And I can respect that. But we want to be able to distinguish between a graph like the one that we have and a graph that might look more like this. Sorry, now I'm squeezing. Where we have, let's say, an open circle at the beginning and the end. There we want to say it's discontinuous at the endpoints. All right? Right? But here we want to be able to say it's continuous. And that definition fails because a function's limit never exists at its endpoints. So how do we modify it? Well, it's really cool, and it's very easy. We just make the limit that can exist equal to the function. So for the left endpoint, right, which we're going to call x equals a, just insist that the limit of f of x as x goes to a from the right, because it's the only direction we can come in, we just insist that that must be f of a. And at the right endpoint, we're just going to use a left limit. So the limit of f of x as x goes to b from the left, as long as that's equal to f of b. So again, what this kind of sticks with is this general idea of if where you're heading is where you end up, then the function is continuous. If where you're heading is not where you end up, then it's discontinuous. All right? Okay, well, pause the video now and write down anything you need to, and then we'll start to apply the definition of continuity. All right, here goes the text. Let's take a look at the first problem where we apply this definition. Exercise 3. Given the following piecewise defined function, determine all values of x at which it has a discontinuity. Give an algebraic reason why it is discontinuous at each point. All right. Ooh, look at this piecewise function. All right. So what we're going to do is we're going to kind of take each formula a little bit at a time and think about it. So let's think about this one. Now remember, I'm going to put this thing up. Limit of f of x as x goes to c equals f of c. All right. Now this thing can fail for a lot of different reasons. Remember, it can fail because this doesn't exist. It could fail because this doesn't exist. It could fail because they both don't exist. Or it could fail because they both exist, they just don't happen to be equal. All right? So there's lots of possibilities here. The first thing that I always want to consider, this is me personally, is I always like to consider places where the function doesn't exist. So when I look at this first formula, 1 divided by x plus 1, the first thing that jumps out at me is x equals -1. Right? That that formula is not going to exist at -1. But that's not a location of a discontinuity. Think about why for a minute. All right. Well, it's not going to become a discontinuity because -1 doesn't fall into this interval. So it's not in this interval. Just abbreviate there. So we're fine there, right? So we're fine. Now let's kind of travel from left to right. Let's just go in this direction. Now the next thing I want to do is I want to think about the cutoff point. I want to think about the cutoff point. So the next thing I'm going to worry about is my -2. Now one thing that can just about dropped my pen. That was humorous. One thing that I can always have happen when I have a piecewise function is that coming in from the left and coming in from the right, I may not be approaching the same value. So let's look at the limit of f of x as x goes to -2 from the left, and let's look at the limit of f of x as x goes to -2 from the right. All right, well, from the left, I'm on this formula, right? Think about that for a minute. You know, as I come here, I'm on this formula. So that ends up being 1 divided by -2 plus 1, and that gives me a value of -1. On the other hand, as I come in from -2 from the right, I'm on this formula, right? And there I'm going to get 4 minus -2 squared. That's going to be the square root of 0, and that's going to be 0. All right? And that is defined there. It truly is 0. So, well, this limit doesn't exist. So we have a discontinuity. We have a discontinuity at x equals -2 because the limit of f of x as x goes to -2 does not exist. All right, so there's one discontinuity. All right, now I'm going to keep moving along. I'm going to hit x equals 0. All right, I'm going to ignore this for a minute. Let's take a look there. Maybe the limit doesn't exist there either. Let's take a look at the limit as x goes to 0 from the left of f of x and the limit as x goes to 0 from the right of f of x. Well, coming in from the left, right, we're on the formula root 4 minus x squared, so that will just be square root of 4, and that will be 2. coming in from the right, we're on this formula, which is 2. Oh, well, that's good. I mean, the limit exists, so limit of f of x as x goes to 0 exists. But f of 0 is equal to 1, right? So we have a discontinuity at x equals 0 because the limit of f of x as x goes to 0 doesn't equal f of 0. We'd have a hole there, right? With a little dot above it. A hole there with a little dot above it. And that's it. Those are all my discontinuities. I have a discontinuity at -2, and I have a discontinuity at 0. Okay? So pause the video now and think about this problem, and then we'll wipe out the text. All right, let's get rid of it. Okay, let's take a look at another problem. I love number 4. Given the function g of x equals blah, 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 what value should be assigned to a to make the function continuous at x equals 1? All right, the reason that I like a problem like A is I'm a very solid thinker. You know, I like mathematical definitions. I love it. So I want the function to be continuous at x equals 1. In order to do that, what's got to be true is the limit of g of x as x goes to 1 must be equal to g of 1. Okay, if this is true, this will force g of x to be continuous at x equals 1. Well, let's just work this through. The limit of g of x as x goes to 1. Right? Well, what curve are we on as x gets infinitesimally close to, but doesn't hit 1? Well, we're on this, right? So this is now the limit as x goes to 1 of x squared minus 1 over x squared plus 3x minus 4. And what's g of 1? Well, that's a. So this is great because now I have a roadmap, right? I'm just going to let a equal whatever the value of this limit is if I can find the value of this limit. Now remember, our first choice always is to do substitution. So if I substitute here, I'd have 1 squared minus 1 divided by 1 squared minus 3 times 1 minus 4, and that will give me 0 divided by 0. Oh, okay, no problem, because that means that a limit technique kicks in. Right, specifically, my trick of factoring and canceling. In fact, right, when I factor, the offending factor cancels. So now a is equal to the limit as x goes to 1 of x plus 1 divided by x plus 4, and that will be equal to 2/5. Right? And look at how nicely that definition of continuity just tells us exactly how to do the problem, right? In order for it to be continuous, the limit of g of x as x goes to 1 has to be g of 1. But then the limit of g of x as x goes to 1 is given by the limit of this rational expression. G of 1 is given by a. And I just keep working it down until I find that a is 2/5. All right. Pause the video now and write down anything you need to, and then we'll clear out the text. Okay, here we go. Boom, gone. Let's do one more problem. Exercise 5. What value of b will result in the following piecewise function being continuous at x equals 4? This is very similar to the last problem, a little confusing in a certain way, but see if you can work through this, okay? All right, let's take a look. This one's a little bit more confusing, but yet it's still the same idea. If the limit as x goes to 4 of h of x is equal to h of 4, then it will be continuous. Now h of 4, well, let's see. 4 is right there. Would be b times 4, which just not B4, it's 4b. So that's h of 4. Now here's what's a little confusing though. That also happens to be the limit of h of x as x comes into 4 from the right. That also is 4b, right? For the same reason, if I'm on x coming into 4 from the right, then I'm on this formula, and since that formula is continuous, I can just put the 4 in, and I get 4 times b. Okay. Now what we really need to do is we need to look at the limit as x goes to 4 from the left of h of x. And what is that? That's the limit as x goes to 4 from the left of the square root of x minus 2 divided by x minus 4. All right, if we did substitution on this, we'd get 0 divided by 0, right? And then, hopefully, our method of rationalizing the numerator would kick in. So we'd get root x minus 2 divided by x minus 4. And I'll multiply by root x plus 2, root x plus 2. Watch how long I keep this limit, right? The limit is x goes to 4 from the left. That's going to be x minus 4 divided by x minus 4 times, look at my parentheses use, root x plus 2. Those will cancel. I'm going to substitute now, which means I'm going to drop the word limit. All right, we'll have 1 divided by 2 plus 2. All right, well, I had to do a little memory management on my computer right there. Let's get back to this. So once we did substitution and erase all this weirdness, what we find is that we find the limit coming in from the left of x equals 4 to be 1/4. But remember, that 1/4 and that 4b now have to be equal to each other. So 4b is 1/4 and b would be 1/16. All right, sorry about the little glitch there. Hopefully that took care of it for a little while. Pause the video now if you need to, and write down anything you have to, and then we'll move on. All right, well, before the noise gets too loud in the hallway, let's wind this lesson up. Wind this lesson up. Oof. It's a Monday. All right, so today we saw one of the classic definitions in calculus, and one of the classic uses of calculus, which is to move from the graphical to the completely algebraic. All right, and in that sense, what we did is we moved from a definition involving lifting our pencil off the paper for continuity to a definition that is exclusively algebraic. If the limit of the function as x heads towards some target value is equal to the function's value, then it's continuous, and if not, it's not. And that definition, that algebraic definition, then can explain every single type of discontinuity that's out there. All right, well, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.